Welcome to the first KISS lecture of 2020. We have a very special speaker tonight, and as you all know, that is Dr. Manan Arya, one of our KISS fellows. Manan has studied the connection between origami and spacecraft structures for a number of years now. He earned his PhD from Caltech, studying large, unfoldable, origami-inspired structures, ultra-thin composite materials, and thin membrane structures. He's now a technologist at JPL, in the Advanced Structures group, and he continues his work studying the intersection of origami and spacecraft design. But Manan is not just a successful engineer. He also does a ton of other cool stuff. You should, if you're trying to write a little introduction for him, you should go check out his website and look at some of the cool photography he has. Or maybe if you need an icebreaker for after the talk to come say hi, you can ask him about his art as an aspiring flow dancer. So I hope you are also excited for this talk on origami and spacecraft structures, and please help me welcome Dr. Manan Arya.
Oh gosh. Thank you all for coming. Oh my gosh, wow, this is a lot of people. Hi, my name is Manan. I'll be talking about origami, how it caught the interests of scientists and mathematicians, and the intersection between that and unfoldable spacecraft structures. So when we talk about unfoldable spacecraft structures, we're talking about things like these. Structures that are too big to fit inside rocket vehicles for launch, so they must be somehow folded up, all tucked up inside, and then unfolded when you get to space. This is a giant radio reflector that was unfolded in 2008. It's about 12 meters in diameter, so that's kind of the length of this room. Or things like this unrollable solar array that was unfolded in 2017. And that's kind of the motivation behind why we want to think about origami and spacecraft structures, is to design new ways of unfolding and deploying these kinds of spacecraft structures. This, for instance, is the solar array on the International Space Station. These were deployed in the early 2000s, and there's actually 8 of these structures on the International Space Station right now. And these, you can see more connections to origami now. These were kind of simply Z-folded up and packaged for launch. There's other examples of origami kind of influencing the design of spacecraft structures, such as this folded array, this folded solar array done by ATK. This is also quite large. Or, let's see. Or things like solar sails, which are large deployable membranes that use the pressure of sunlight, the momentum of sunlight, to propel themselves through space. This was actually a solar sail, the first solar sail ever unfolded in space by the Japanese space agency called Icaros. And it's 20 meters in diameter. This thing is gigantic. And it was folded up in a very nice origami sort of way. A solar sail that was unfolded by some folks just down the road, the Planetary Society. Oh, by the way, this is a picture of Icaros. It was a selfie that it took of itself in space. I was talking about the Light Sail project, which was a solar sail that was deployed by the Planetary Society, which has its headquarters just down the road. And this is a selfie that Light Sail took in space. And you can see Light Sail and Icarus are both using some form of origami fold pattern to package up inside their launch vehicles. So the examples that I've shown you have been rather simple origami fold patterns, right? We had the ISS solar arrays, which are simply Z-folded. It's just parallel mountain and valley folds arranged like that. The Ultraflex and the Megaflex solar arrays that I showed you were simply fan-folded, so it's very much like Z-folding, but in a radial sense instead of in a parallel sense. And Light Sail was simply double Z-folded, so you Z-fold along one way, and then you Z-fold along the other way, kind of like the way you'd fold a map, right? And then Icaros was just Z-folded as well. So each quadrant of Icarus was Z-folded, and the entire thing was wrapped up around itself. So the thing that I want to try and address today is what kind of origami designs influence people when they designed spacecraft structures? And how did we get from ancient Japanese paper folding to using origami in spacecraft structures? So we're going to start at the beginning. We're going to start with where origami started. And unfortunately, there's not too much documentation about where exactly origami started. Many different cultures had traditions of paper folding or cloth folding, which is very similar to paper folding. And the first real evidence we have of sort of paper folding in Japan starts off in the early 1600s. The first published instruction manual of how to fold origami was this book that was published in the late 1700s in Japan. And interestingly enough, as I was doing this research, I found that there was this German educator named Friedrich Froebel, who in the 19th century came up with the idea of kindergarten. He was kind of behind the movement for kindergarten. And one of his interests was to get K-4 students interested in paper folding as a means of discovering geometry and geometrical relationships on a 2D plane. And this movement found its way into Japan and kind of influenced the Japanese ideas of paper folding as well. And up until the 19th century, paper folding had kind of become established as a toy, as a recreational pastime. It had ceremonial uses in Japan. And also, interestingly enough, props for magicians and stage show artists who would perform on stage. And there were a number of traditional origami designs kind of set by this point. And you all know the paper crane. And it wasn't until kind of the 20th century that we started seeing origami become more complex beyond these simple designs. The first people to start thinking about paper folding in a mathematical sense was actually this Indian educator who was working in Madras, India in 1893. He wrote this book called Geometric Exercises in Paper Folding. And this was a book about how to discover things about Euclidean geometry, things about geometric constructions, but through paper folding. I think everybody has thought about or read about geometric constructions through compass and straight edges, but it turns out you can actually do a lot of those types of constructions using paper folding. And this idea of using paper folding to come up with geometric constructions carried on throughout the century. Margherita Belloc, who was an Italian mathematician at the University of Ferrara, she used these ideas to come up with this theory that said you can actually solve cubic polynomial equations using paper folding, which is something you cannot do with just a compass and a straight edge. And later on, in the early 80s, Humi Huzita and Jacques Justin, who were two mathematicians in Italy and France respectively, came up with ways of describing what you can construct on a 2D plane with paper folding in terms of geometric constructions. But this is all on a 2D plane. This is all sort of Euclidean geometry type thinking. And I personally am more interested in what can be done in terms of sculptural origami and origami designed forms, and not just the 2D plane. So we're going to move on from this chapter in origami mathematics and talk about this gentleman, Akira Yoshizawa. Now, if you talk to an origami folder today, they will most likely identify Yoshizawa as sort of the grandfather of modern origami. He was a Japanese man living he was born in 1911, and he started folding in the 1930s, all self-taught. And his contribution to the field of origami was taking it beyond just sort of children's crafts and taking it to an art form where it was almost sculptural, right? You can see this bull or this gorilla that he's folded. And he was actually the first one to kind of insist on the idea of not cutting paper. Previous to this, Japanese origami involved cutting paper, and if you've read any books about origami, that's one of the rules of origami is that you can't cut paper. He was kind of one of the pioneers of that rule. He also pioneered the concept of wet folding, which is dampening the paper in order to get these amazing sculptural forms. And most importantly, I think, he established a graphical notation, a diagramming system for documenting paper folding. And this really allowed origami to be published and communicated and disseminated. You've all probably seen these kinds of diagrams where a system of lines and dots and arrows showing you the steps you need to do in order to construct origami models. So Yoshizawa is where the history of modern origami really starts. And he was brought to the West. He was brought to the attention of Western thinkers by this man over here, Gershon Legman, who was an American living in the south of France in the early 50s. He was a folklorist, and he was sort of enthusiastic about origami. But he discovered Yoshizawa's work and brought it to Amsterdam in 1955. Around the same time, this man, Robert Harbin, who was as best as I can tell, a South African magician. He actually invented the magic trick where a person standing in 3 boxes gets shifted. One of the boxes in the middle gets shifted over. He invented the magic trick, but he was also an enthusiastic origami folder. And he published this book called Paper Magic, which documented a lot of traditional Japanese foldings and brought them to the attention of the West. And Lillian Oppenheimer, who was a New Yorker, she actually became so interested in origami, she went to London to meet Harbin. And when she came back to New York, she founded the Origami Center of New York in '58, which is now Origami USA, which is a very large society of origami enthusiasts within the United States. And she actually brought Yoshizawa's work to New York in 1959. And this is when people's impressions about origami, right, started shifting from it just being paper folding or something to do on stage to sculptural art forms. The first engineer, best as I can track, to become interested in origami was this man, Ron Reck. He was a computer scientist. He was a sort of a numerical geometer. And he started coming up with origami designs in the early 1960s. He was working at the University of Utah. There he is, looking very 70s now with his creation. This is called the kissing cones, and I think it's rather pretty. He was also experimenting with curved folding rather than straight folding. But his most famous creation is this thing over here, the fold pattern for which I'm representing over there. It's a system of triangles that is now called the Ron-Reck tessellation, or the Reck tessellation. It's a system of triangles that allows paper to be sort of compressed in that manner that you just saw in that video. He did this wonderful thing where in 1992 he released a video, which I'm going to encourage all of you to go check out. It's called Paper and Stick. And he documents his work that he was doing between 1960 and 1966 in this video. Unfortunately, the sound on my computer is not working, so you can't hear him narrate the video. So I'm just going to tell interested parties to Google that title, and you can go check it out himself. It's wonderful watching him discover new ways of folding paper, of creating these kinds of mechanisms and these engineering artifacts using the ideas that he's come up with. The other person that I'd like to highlight who was working in origami at the same time is David Huffman. David Huffman was a computer scientist, initially at MIT, then he moved to UC Santa Cruz. And if there's any computer scientists in the room, you definitely know David Huffman. He invented Huffman coding, which is kind of the basic computer compression algorithm that underlies kind of your favorite file formats like JPEGs and MP3s. But he actually got interested in origami, and he met Ron Reck in 1968, and he actually spent a sabbatical year at the University of Utah with Reck in 1973. A sabbatical year for the non-academics in here is a vacation for a professor where you go and spend a year away from your students, escaping all your responsibilities, and just have fun. So that's what David Huffman decided to do with Ronald Reck at Utah in 1973. And Huffman invented and came up with these amazing origami tessellations like that, and also more curved folding, things like the example that you see him holding over there, or these kinds of spiral curved foldings over here. He actually only wrote one paper on origami in 1976, and it is a wonderful paper. If you read this paper, it is completely dense. Apologies for the non-mathematicians in here. This is the only slide with equations on this in this talk. But Huffman actually kind of took a very mechanical approach, a very mechanician's approach, to describe how origami moves, how a degree 4 vertex, which is a point in origami where 4 creases meet, how they move depending on how much you're folding them. And these equations describe that. He also, in the same paper, wrote about curved crease origami and how and what the form of these curved creases needs to be. All of this is coming from, by the way, this paper over here, and you can go check that out. But the first person to kind of think about origami in terms of its applications to spacecraft was this man over here, Koryo Miura. He was a Japanese physicist working at the Institute of Space and Astronautical Science, which is now part of JAXA. And he was a physicist, and he came up with this fold pattern, which is now called Miura Ori. So it's named after him. Miura is his name. Ori just means fold. So this is the Miura fold. And it's a fold pattern that does this. It's kind of the hydrogen atom of origami engineering. It's kind of the simplest origami engineering pattern that you can think about. It kind of leads to many more complex ideas if you just continue thinking about it. But the way Miura came up with this fold pattern is fascinating. This is a fold pattern that has 1 degree of freedom, which means it kind of folds and closes very nicely without you having to manage a very large number of folds. It is rigidly foldable, which means if you constructed this fold pattern out of steel sheets with hinges, it would fold very nicely. I have an example of this fold pattern, and I'm going to pass it around. Please don't break it. But it looks something like this. This is a very small unit of Miura Ori, and I'm going to pass it around, and you can play with it. It is possible to break it, so be gentle. Go ahead. But I'd like to tell you the story of how Miura came up with this fold pattern. He, like I said, was a physicist, so he was interested in physical problems. In 1970, he was studying this problem, the problem of what happens if you take a thin-walled cylinder and you compress it. You put axial load into it. And what that cylinder wants to do is buckle into this network of triangles. This is called the Yoshimura buckling pattern, and there was another Japanese physicist who discovered that. But Miura thought to himself, well, if a cylinder wants to buckle into this pattern, if you apply loading to it, what does a plate, what does a thin sheet want to do if you apply axial loading to that? And Miura actually used sort of physical, mechanical equations that people who come through Caltech would use to figure out that this is kind of what a plate wants to do when you apply this equibiaxial load to it. It wants to buckle in this pattern. And this is exactly the Miura Ori pattern. And he kind of ran with it. He took this pattern and he said, oh, why don't we build spacecraft out of it? And in 1985, he actually proposed using Miura Ori for packaging a solar array. And JAXA actually built and launched a solar array based on the Miura Ori. Unfortunately, I couldn't find any great images of this experiment. This is kind of the best image that I could find. If somebody has better images, please let me know. I managed to use the Wayback Machine on the internet to go back and mine old JAXA websites for these pictures. But this is what that experiment looked like. It was launched in 1995 on the spacecraft called the Space Flyer Unit. It was launched by JAXA. And this solar array, this experimental solar array, was folded using exactly Miura Ori. And the fun thing is, it was actually retrieved, the space flyer unit was retrieved by the Space Shuttle Endeavour in 1996. And now this sort of pioneering origami space experiment is sitting at the Natural History Museum in Tokyo for you to go see. Unfortunately, I don't think they've deployed the array there, which is a shame, because I'd like to see that array deployed and more pictures of it. But I find this story fascinating of somebody coming up with a fold pattern using entirely physical mechanical equations and then launching it into space and showing a new way of folding solar arrays. Around this time, these people, Ronald Reck, David Huffman, Miura, they were coming up with ways of using origami to create engineering structures. But at the same time, there were engineers and mathematicians who were using mathematics to come up with new origami patterns. So in the 70s and 80s, a number of mathematicians, 4 of whom I'm listed over here. John Montrell was a mathematician and educator. Peter Engel was an architect. And Jun Meikawa was a nuclear physicist, or is a nuclear physicist, now origami fold. And Robert Lang started off doing laser physics here at Caltech. They started using mathematics to design new ways of folding origami structures that were much more complex than previously. So here, for instance, is a fold pattern that Robert Lang developed using sort of symmetry arguments, building up from existing origami structures to fold this really remarkable sea urchin that, in terms of origami complexity of sculpture, is fascinating and amazing. And then Robert Lang also went on to create other ways of using mathematics and optimization to create new origami structures. If you go to his website, actually, he has an amazing list of some really wonderful sculptures that he folded using these kinds of mathematics. And in 1989, there were enough scientists and engineers and mathematicians interested in origami to actually have a meeting. And this meeting was held in Ferrara, Italy. It was organized by Fumiaki Ozita, who I mentioned as being one of those mathematicians interested in geometrical construction through origami. And this first initial meeting was so successful that it spawned an entire series of meetings that have continued meeting, settling on a sort of roughly 4-year time frame between meetings. And the last one was held in Oxford in 2018. And this is a meeting where mathematicians, scientists, educators, engineers, origami artists come together and talk about these topics. There's also a similar conference that the American Society for Mechanical Engineers hosts every year, and that is also fascinating. The first meeting, the proceedings from that meeting are impossible to find. It's a very thin volume. It was self-published by Ozita. It was edited by Ozita. And I can't find a copy. If anybody has a copy, please, I would love one. The same thing can be said of the second meeting. There's not too many proceedings floating around. But as you move forward in time, the proceedings become easier to find. They also become bigger. So you have a slimish volume for number 3, whereas for number 7, it's 4 gigantic hardback books. So the amount of literature, the amount of material being produced about the mathematics and science and technology of origami just starts to increase or starts to blow up in 1989, which is why I'm not going to be talking about that. It's just too much to talk about. I can't tell you the complete story. So what I'm going to do instead is I'm going to pick up one thread of that story, of how origami influences engineering, and talk to you about that thread. And the reason I'm going to pick that thread is because it's a very selfish reason. It's a thread that I use in my work at JPL. And that has to do with designing wrapping patterns for origami. These patterns take a flat sheet of paper and they wrap it around a central prism. I've got some examples of that, and I'm going to pass those around as well, and you can play with them. Again, if you pull on it too much, it will break, so don't pull on it too much. I'm going to pass it around over here, and maybe one for that side as well. Let's see, which one is interesting? This is interesting. So these kinds of origami patterns take a flat sheet of material and they wrap it such that it wraps around sort of a central prism or a central cylinder. And I can't definitively say who first discovered it. The first published material I can find about these origami wrapping patterns are a series of patents, a series of US patents by Huso, Lanford, and Scheele. Lanford actually invented this amazing apparatus for folding up these wrapping structures, system of hanging weights, such that you put tension on your material, and then you turn a central hub, and it kind of wants to wrap up nicely inside there. Scheele actually went a step further and had these sort of reverse folds along the fold line, so you end up with a better compaction. The model that's going around that side has those kind of reverse folds as well. And then in 1992, Simon Guest and Sergio Pellegrino came up with this way of algorithmically designing these fold patterns. Previous to this, the origami wrapping patterns were kind of empirically discovered. People would fold things and see what they wanted to do. And in 1992, Guest and Pellegrino actually came up with a mathematical algorithm that would produce these fold patterns. And you can see this was produced kind of algorithmically because there's these curves in the fold pattern that allow the structure, when wrapped, to wrap up in spirals, right? And that wrapping up in spirals is important because it allows for thick materials with actual thickness to them, to be folded. The other thing that this algorithm does that Simon and Sergio wrote is that it makes sure that the length of the fold lines does not change between the unfolded state and the folded state. And that's important because that means the material is not stretched, it is not torn when you fold it, it is not compressed, which means I can take the structure and I can make it out of something a bit more stiff than paper, right? And that was really important. Almost contemporaneously with Guest and Pellegrino, these two origami artists, Jeremy Schaefer and Chris Palmer, came up with this kind of a folding pattern, which I'm also passing around. I've got an example of exactly the pattern that Jeremy Schaefer and Chris Palmer came up with. It's made out of this aluminum foiling material, and you can play with that. Jeremy Schaefer is an origami artist and a performer. He performs on stage with origami. Chris Palmer is an origami artist as well. And they published their design, or rather their design was published in 1997 in a book that Robert Lang was editing. And Schaefer and Palmer were influenced by this design for an origami rose by Kawasaki. It's called the Kawasaki rose. And you can see in the center of the rose, there's these 4 petals that come out. And this is very reminiscent of that wrapping pattern that Jeremy Schaefer and Chris Palmer came up with. Jeremy Schaefer actually has a very active YouTube channel, which I encourage you to go check out. That's Jeremy Schaefer. Jeremy Schaefer and Chris Palmer chose to call these wrapping patterns flashers, and that's the name they came up with. I try not to use that name because if you write in your proposal to JPL, oh, I'm going to make a flasher, it doesn't sound as nice. So I use origami wrapping patterns. In 2002, this Japanese master's student named Nojima actually came up with a whole bunch of origami wrapping patterns that were kind of, he wrote equations to generate these spiral forms, and then he found that by imposing certain restrictions on the angles where these folds met, he could get these spiral forms to fold up nicely. And he also was, I think, the first one to show that if you made cuts along these spiral lines and then joined the structure back up, you'd end up with these bowls. You'd end up with cones. that could be wrapped up compactly. And that's important for spacecraft structures because we care a lot about parabolic structures that can be folded up. And in 2013, Shannon Zerbel, who was a graduate student at the Brigham Young University in Provo, Utah, Robert Lang, and a bunch of engineers from JPL wrote a paper where they took kind of the flasher design that Jeremy Schaefer and Chris Palmer came up with and wrote an algorithm, wrote a computer program that would generate a whole zoo of these fold patterns. So again, this fold pattern is generated using an algorithm that makes sure that when folded, these structures wrap up in these very nice spiral formats. So there's spacing between the various layers, but also making sure that there's isometry between the flat state and the folded state, which means nothing needs to stretch, nothing needs to tear, and nothing needs to be damaged. This is actually this is Shannon over here unfolding one of her structures that she's designed. And they also proposed using this kind of a structure for a solar array in space. So here you can see a sort of an artist's conception of that solar array being unfolded with a truss structure on the outside. This paper, this work that Robert Lang and Shannon Zerbel did on these kinds of structures was done with the help of some JPL engineers. And this is where I kind of entered the picture. These JPL engineers were working on a project called Starshade, which I'll talk about in a bit. But first, I need to talk about this mission called R3D2. This actually launched last year that used an antenna reflector made of a membrane that's folded up very much like in that spiral format. It actually unfolded out to be about 8 feet in diameter. This was launched in 2019. This is how it unfolds. And unfortunately, because this was a DARPA project, I don't know what happened to the spacecraft. There's no confirmation whether it unfolded correctly or not. But it's cool to think that this wrapping pattern that was designed has actually flown in space now, though I don't know if it unfolded correctly or not. I mentioned star shades. Star shades are the project that the JPL engineers on this project were working on. And star shades are something that I'm working on right now that uses these kinds of origami wrapping patterns. So a brief introduction on star shades. A star shade is this structure over here. It is a way for a space telescope to be able to take pictures of planets around other stars. It turns out that there's a lot of planets around other stars. It's really hard to take pictures of them because these planets tend to orbit these bright, pesky thing called stars, which are about 10 billion times brighter than the planet. So what you need to do is you need to have a light blocking device in space that blocks out the light from the star so the telescope can see that planet. The way the physics works out is that star shades need to be about 30 meters in diameter, about the size of a baseball diamond. So you need to package them up to launch them. This is how the star shade concept that's being studied at JPL right now is being packaged up. It has a number of these petals on the outside, and they unfold first. And then the second step of unfolding happens, which you just saw, where the inner disk unfolds out and puts the petals in their proper location. It's that second step of unfolding the inner disk that is what we'll be talking about next. But yeah, the star shade unfolds and then blocks out that starlight. And hey, look, planets. And that's the concept. But the thing that I'm using the star shade, this wrapping pattern, this origami wrapping pattern for, is this step of unfolding the inner disk of the star shade. So we actually built a full-scale prototype of this inner disk system that's about 10 meters in diameter, or about 30 feet in diameter. It folds up to this very compact form. It's hard to tell from these pictures how big this thing is. So here's a picture with Kenzo, who is a regular-sized human being for scale. And this structure has inside of it this origami packaged opacity cover. We call it the optical shield because it shields the telescope from the light of the star, and it folds up in a pattern that at this point you should be familiar with. It's this origami wrapping pattern, a system of mountain and valley folds that allow the structure to be wrapped up into this compact form. This is something that I designed using a modification of the existing origami design algorithms that have been developed. The neat thing about the structure is that it's not actually flat when unfolded, it's actually conical. So you have to do some clever tweaks to the existing algorithms to get a conical structure to fold up into this compact format. And because this is an engineering structure, it actually is filled inside. This is a picture of how we constructed that. It's actually filled inside with frames and ribs and a skeleton that gives us some stiffness. And remember that condition about isometry, the condition about making sure nothing stretches when you fold it versus when you unfold it? That's what enables me to put all these aluminum structures inside there without ripping them to shreds. Here's a video of this structure unfolding. I was actually in Colorado last week unfolding the structure, which is why it looks like I'm wearing the same shirt that I'm wearing right now. It unfolds over about 30 minutes, so this is very sped up. And when it reverses back that quickly, that's just a video trick. It actually takes about 5 hours to fold manually. All these strings that you see, all these weights, are counterweights to try and balance out the weight of the structure. We want to try and simulate deployment in 0G, so all of those strings run over pulleys overhead that lift up the structure, negate exactly the weight of the structure, so we can study the unfolding of this system. One of the things that I did not mention about Starshade is that it needs to be extremely precise. When unfolded, the perimeter of the structure needs to be accurate to within about 150 microns. That's about the width of one of these hairs over here, over 30 feet. And over the past year, we actually demonstrated by unfolding the structure many times that this is actually accurate to within that 150 microns, which I think it's kind of remarkable, like that the structure can be unfolded at that level. Now for something completely different, talking about flowers. This is one of my favorite species, favorite genuses of flower. It's called the Datura. It unfolds out to look like that. When it's blooming, it's got this very nice spiral format that may be reminiscent of the wrapping patterns that I was showing you. And I was looking at these flowers, which, by the way, grow wildly in Southern California. I bet you anything there's a bloom within like a mile radius of here. I was looking at these flowers. These pictures were actually taken behind our Starshade lab at JPL. And notice that when it's almost blooming, it's got this kink in the middle that makes sure that the flower doesn't kind of flop open. It gives this stage of the flower some structural stiffness. And I was thinking, hey, I can design an origami wrapping pattern that is conical when unfolded. Can I design an origami wrapping pattern that's got this kink in there such that the origami pattern is kind of, when fully unfolded, kinked in a way? And it turns out you can actually design these origami wrapping patterns that are kind of kinked in that way. It's got, in the central part, these kinks that make sure that the structure doesn't actually ever go flat. It stays in this sort of rippled, corrugated, non-planar form. And you may be wondering why anybody would want to do that, why stay in this sort of rippled, corrugated, non-planar form. And that's to do with providing the structure with some stiffness, right? Because this thing is corrugated, because the structure is ruffled, it wants to stay in this form. Whereas if you imagine this was completely unfolded flat, it would just want to flop over. And what this means is we can do away with sort of those trusses that you were seeing on the periphery of the star shade and the trusses that you were seeing on the periphery of the solar array that was proposed by Shannon Zerbel. And maybe we can make origami structures that can support themselves and not need anything else. But it still folds up in this compact spiral format that I was showing you. So obviously the next thing to do is to try and build one of these things, and that's what it looks like. This is made of carbon fiber and brown packing tape. So it's an initial model. And the neat thing about the structure is it does exactly what I wanted it to do. It unfolds out, and right now it's only resting on that sort of acrylic base bead. It's supporting itself, it's supporting its own weight. And yet it can be packaged up very nicely like I'm about to show you over here. And by the way, completely coincidentally, I'm wearing the same shirt. I apparently only own one shirt. But the way you generate these kinds of patterns is by working from the center out, generating each ring as you go along. And the math becomes slightly more challenging than if you're just dealing with a flat sheet of paper. You know, we understand how flat sheet of papers work, how geometry works on a flat sheet of paper. Designing these structures to wrap up in those complicated, in the spiral formats, while making sure that there's no stretching going on between these two states, and also making sure that we get this sort of corrugated rippled format. That ends up being a bit more fun than just designing a flat sheet of origami. And here's some math. It's there's some optimization going on. There's some making sure that triangles remain the same, and you can write this math in terms of MATLAB code, which I've done, and generate a whole zoo of origami wrapping patterns that somehow just lock into this non-flat shape when fully unfolded. You can also prescribe the height of each one of these things when fully folded, so you can get some things that are really, really shallow like that, or some things that are really steep, or some things that are kind of a mix of both. So that's fun. And this will be something that I'm going to be pursuing going forward, trying to think of ways of designing solar arrays using these kinds of structures, because it turns out you can actually get very lightweight solar arrays if you do away with trusses and booms and other kind of support structures and just have things that are supporting themselves. Anyways, so we're gonna try and sum up the story that I told you. We started off with traditional origami fold patterns, and we saw how Yoshizawa kind of pioneered modern origami folding. We saw how Ronald Reck and Miura took origami and applied sort of engineering methodologies to come up with new forms. And then also how origami has been used in sort of simple formats for unfoldable large structures for spacecraft, like these solar arrays or this solar sail. And then in things that I'm working on these origami wrapping patterns for things like starshade, which can end up producing very large, very stiff structures for space applications. Hopefully this was an interesting talk. I'd love to take questions at this point.